Okay. Good morning, everybody. How is the atmosphere? Everybody relaxed? Somebody excited? I'm excited. I am very excited. I will tell you why. But first, dear finalists, dear members of the jury, dear guests who are present here today at Technical University, but also who are present via live stream. Welcome to the scientific presentations. And thereby the start of the big finale of Evergreen Prize for Innovation 2025. My name is Hans Pachner. I am head of R&D for HS Timber Group, a company whose basically sole shareholder, Evergreen Prize Stiftung, follows the mission to advance education, innovation, and research. And also who happens to be headquartered just over there. So if you're asking where I'm working at, it's this building right over there with the gas front. The mission to advance education, innovation, and research is not just words for us. It is written into the charter of the foundation, and it is lived through projects that range from building schools in Africa and India, to supporting a 9-year, 10 million euro basic research project here at the Technical University of Vienna. Markus Lukaciewicz's Christian Doppler laboratory called WoodComp 3D. Those who don't know it, maybe you want to Google it. It's a pretty cool project that Markus and his team are doing there. WoodComp 3D. And of course, it is what we're doing here today. It's Evergreen Prize for Innovation. Before we proceed, I want to say a heartfelt thank you to the Technical University here, who also provided us with the facilities today, and who proved to be a very strong and reliable and great partner in doing research over the last years. How did we come to this day today? We opened the application for Evergreen Prize for Innovation last year, and we received almost 40 applications. 30 of them were scrutinized by our jury, and this is now the persons whom I would like to introduce. We have with us today Samsa Auvinen, who is also the chair of the jury. The driving force in our industry's Brussels activities, and you have functions in both the Sawmillers Association and the Wood Industries Association, US and COA, and you're a board member in various industries, and I think also dealing with some startups. So he is bringing the industry perspective. The next lady at Usado, I hope I pronounced it right. Next lady, she is CEO and president of the Sustainable Forestry Initiative. She's original Canadian. And the SFI, the Sustainable Forestry Initiative, is what it sounds like to be. It is a certificate scheme for sustainable forestry. And Katie tonight will also hold the keynote speech in the city. Thank you, Katie. Next, Professor Josef Füssel, Professor of Structural Simulation and Timber Engineering of the Institute of Mechanics and Materials and Structures at the Technical University, and also our authority on the computational modeling of wood, and also heavily involved in the Christian Doppler laboratory. Andrea Kuttner, I don't really know if I need to introduce you, Andrea. I think everybody in Europe seems to know you. She is director of InnoVinU and professor of wood science and technology at the University of Primorskaya in Slovenia. And last, but of course not least, and also a person who probably does not need to be introduced, it's Professor Alfred Teichinger, my Professor Alfred Teichinger, who also I was studying also 5-6 years of wood technology at Boku University under Professor Teichinger, and he of course was professor for wood science, and I mean he's retired now, but he has now time to write books and bike trips. Yeah. Thank you. this means 30 minutes with a hard stop. This 30 minutes includes a short video that we shot at your institutions, which basically outlines what you're doing, followed by your presentations and Q&A. In total, 30 minutes. Ulrike will give you a hand sign at 29 minutes and another hand sign at 29, a hand sign at 25 and another one at 29, so you know roughly where you are. The more time you need for the presentation, the less time is for the Q&A. After we hear all 5 teams presenting their project, I will take the jury and we go over there for the closed jury deliberation. And what happens there is, of course, of most interest for you. The jury will decide 2 or 3 teams that are going to be eligible to win the big Evergreen Prize tonight. This choice will be secret. We will not tell anybody until after all of those 5 teams, all of you 5 teams, presented tonight in City Hall. So we want to keep the suspense up. We want to give also everybody the chance to really pitch your idea in front of a big audience. And when I say big, I mean big. We are expecting 850 guests from 50 countries around the world, and this is going to be a top audience tonight. After you have the pitches in front of the audience, we are going to unveil who is going to be the jury's favorites, and then among those jury's favorites, which again might be 2 or 3 teams depending on the jury, then the audience will vote. And the audience will vote on where do they see the bigger, this is what we are going to ask them, where do they see the bigger potential. And then the audience winner wins. Before I stop, one word of encouragement. Only one team tonight will walk away with 300,000 euros, but all 5 of you who are here today, for me at least, are winners, and you should feel like winners already. You came to the end, and you're the finalists, and you are going to be on stage in front of the global wood community. We are going to have C-suite executives of the biggest sawmilling and wood processing corporations of the world here tonight in Vienna. We're going to have top policymakers in Vienna. You are going to present in front of other researchers. There's so much potential for you to make an impact, make an impression, use it, go out, talk to everybody, and just enjoy yourselves as well. Before we start with the presentations, I have 3 simple and easy rules. First of all, the teams are going to present in the order as we received their applications during the application phase. We have, as I said, 30 minutes total per team. Then during the Q&A, only the jury may raise questions. And since we are live streaming, I would ask everybody to use the microphones, including the jury, for the questions. Good. I have spoken long enough, and without further ado, please welcome Max Hamilton and Tobias Engel from the University.
At Boku University in Austria, a research team led by Max Hamreiter focuses on the use of branch wood as a raw material. A 3-dimensional measurement captures the geometry of the entire tree with special attention to its branches. The aim is to process this irregular and curved resource into high-strength wood-based products. The branches are processed into strands, which are dried, sorted, and pressed. Stranding is a very efficient technique from the OSB process. It can recover up to 95% of the input material. However, branch wood, especially from hardwoods, has not been used this way so far. The potential of the material is determined by meticulous analysis throughout the entire process. The analysis begins at the nanometer scale and extends to the macroscopic structure of the tree. Their work lays the scientific foundation for integrating branch wood into long-lasting wood construction products such as panels, beams, and future composite materials.
Dear esteemed scientific jury, good morning to everyone in the audience, good morning to everyone attending this prize event online. For Max and myself, it's a great honor to be here today, of course, and present in front of you and to answer your question. Honestly, yes, I'm very excited actually, especially for me as a PhD student, I'm very excited to be here. But there is actually one thing I'm even more excited, and that is the figure of 3 trillion. There are about 3 trillion trees on this planet doing all these great things that are so vital for us humans. Statistically speaking, that means about 400 trees per person. 400 trees for Max, 400 trees for you, 400 trees for me. And now if you visualize your trees, your 400 trees, they do not only consist of stem wood, but they also do consist of huge amounts of branch wood. And these branches, they are the main focus of the next minutes. But why should one care about branches in the first place if we have stem wood? Well, looking into different reports, we found out that, or we learned actually that there's a limited additional harvest potential within the European Union. So currently we are at about 80%, strongly depending on the region you look at. And for example, in Austria, this figure is already 97% in recent years. To sum up, there's only very limited additional potential to use from the wood provided by our forests. On top of that, climate change is even putting more pressure on our valuable forest resources, and that's a shift already taking place. For example, forest stock figures here for Germany, we see that there's a decline in spruce wood already, and there's an increase in hardwood species. In this case, there's oak and beech, for example. This trend is going to, or is expected to continue till the end of the century, meaning more deciduous trees, fewer conifers, and deciduous trees, that what your deciduous trees tend to do, they do grow more branches. So we have to face a new materiality. Then, as wood scientists, we do not only care about the wood availability, but we also care about how wood is used. And everyone who has some background in wood science or any forestry studies knows cascading use of wood is key. Starting with primary wood processing, continuing into high-value construction product, eventually ending by burning, and burning ends any circularity, at least for a very long time. So again, we looked into figures from the European Research Center provided, looked into the timber and construction share within the European Union, and this is below 3%. Of course, again, that strongly depends on the region you look at, strongly depends on your classification system, but the point here is there's a lot of potential to grow for wood in the construction sector. On the other hand, again, a figure from the Joint Research Center, the primary wood for energy share, so the wood used without prior material use for energy in the European Union, is up to 50%. That means this wood has not been used as a material before. And within this 50% share, within this orange box, there is also around 80 million cubic meters of hardwoods per year burned directly. And within these 80 million cubic meters of hardwoods, there are also the branches we do care about. So that is actually what we call the hidden potential. And for conifers, you see here on the left-hand side, for conifers, this hidden potential makes up to 50% on average on branches, but for deciduous trees, this can make up to 35%, depending on tree species, the size, class, and location. This here is an example for beechwood, for example. So this motivated us 3 years ago to look closer into these branch wood assortments. It was also the main motivation, and we directly wanted to start producing panels and beams, so that's what we wood technologies also like to do. But then we had to learn there is actually not a lot of basic material properties investigated so far. So in comparison to Stanford, there was only a few research done. So we had to learn, we had to make one step back in order to move forward and do this labor-intensive material testing first. Or to put it in the words of my supervisor, Professor Conrad, es gibt's ja nicht. So he was very surprised that this is the fact actually. There is not a lot of research done on this topic. So that's where our journey looking into branchwood from deciduous trees began 3 years ago. We teamed up with the Institute of Forest Growth at Boku. We did some 3D laser scanning. And so we captured the full tree in a digital model. And this made it possible to trace back the different tensile, compression, and three-point bending samples into the standing tree. And that allowed us to find out, for example, that a steep branch does differ from a flat branch, and in terms of mechanical properties. And it also made us possible to find out, for example, that branches do have a higher wood density overall for oak and beech. But what you expect with high wood density? Some would expect higher strength value, but we found out that they are only comparable. And for example, for tensile strength, the beech branch was 20% below the stem, the corresponding stem wood. But overall, if you look at this material property chart, applied as beams or panels, the orange part is the branches. They definitely can compare with the stem wood, so they do have a technological potential when it comes to a resource-efficient use. We looked one level deeper, impact bending strength this time, and we again found out branchwood does actually have a lower impact bending strength than stem wood. So what could be possible reasons? We looked into fiber length, for example, and we found out the fiber length of branchwood is around 25% lower than the one in stem wood. And then the most recent, and also for me the most exciting part happened some months ago. Again, collaboration with physicists from UBM. We went together to the synchrotron particle accelerator in Hamburg, and we looked into branchwood on the cell wall level. We again compared steep branches, flat branches, compared to the corresponding stem wood, and very exciting to me, there are differences also depending on the growth angle. And overall, flat branches in for oak, for example, they had the highest overall orientation on the cell wall level in the flat branch, also higher than the stem. So in summary, we really already learned a lot about the material properties. We couldn't now finally wait any longer and start with processing the materials. So two very motivated master students looked into different splitting and disintegration technologies available, which might be suitable for our branches. And they also found one, you see it here in this video. It's called the microfiber technology. It was developed by Woodcake Glass and Boku some years ago, and we adapted it to our branches. We were also successful in this lab trial to produce some panels. We tested them. We also brought some samples in the back for later for the coffee break for you to investigate. But we had to learn they do come along with a huge variability actually. So these microfibers differ very much in length and also cross section. And then again, brought us back to the question, what is a suitable disintegration technology for our branches? And frankly speaking, our approach so far completely failed for beech branches. So back to the start, and luckily, when it comes to disintegration technologies, Max is an expert, and let's go for it.
Thank you, Tobias. I think you're absolutely right. I'm not the only expert on disintegration technologies, but I spent a lot of years investigating established disintegration technologies for current engineered wood products. And right around the time when the Evergreen Prize was announced, we were revisiting existing technologies to disintegrate brown wood. As the wood technologists in here might already know, but the sawmilling process and the veneer filling process require homogeneous raw materials. So for our crooked and bent branches, we thought, okay, splitting technology works in general, but it's rather slow in the field for wheat, for example. What about the straining process, which we know from oriented strain board and laminated strain board? And the assumption here would be, or is, that we will be able to not only process stem wood with this process, but also branch. And luckily, we also have some experience already improving the straining process and the products from the straining process as well. So while Matthias was looking at branches, two of our other PhD students, Lucas and Andre is here today as well, so you can talk to him in the break if you want. And they were looking into improving the application potential of strain-based products. In a project called Unistrand, which is led by Professor Konrad, around 15 project partners are trying to improve the application potential by unidirectionally oriented the strands and by differentiating density or by creating different density panels, also improving the range of strength classes that we can use. Furthermore, the aim here is to create an intermediary product that can be used for a cross-laminated composite and can exist along the current shooting star in wood construction cross-laminated timber. From literature, we know that with panel density, we also can change the performance of the panels, and we try to build on this knowledge and adding the unidirectional orientation. Most recent findings from Lucas in that case, I want to show really quickly here is that, I guess it's not a big surprise, but we were able to create different density panels. But the interesting part, and I think also the biggest takeaway here is that we are actually able to create different strength classes along bending, compression, and tensile strength, and same for the modulus. If you look at the red stars, you can see that we are actually able to design strength classes depending on the purpose and the final application. Therefore, we can use the material more resource efficient only where it's actually necessary. And before we go into the way forward, we are roughly 12 minutes in. I want to take a short mental break. So here's a picture of another student taking a rest on one of our microfiber panels. The way forward. When the Evergreen Prize was announced, we thought, okay, this combination of projects, Unistrand and strong hardwood, might be the right case for applying to it. As both projects are ending this year and funding is limited, in order to combine this knowledge into branch up, we need additional funding. If awarded, we will create a new project team, hiring a new PhD candidate. This is also where most of the funding will go towards to, paying the salary of this PhD candidate. The project team at BOKU will be complemented by Tobias and myself, and academic supervision will be provided by Professor Kohn. The PhD student will also be embedded in the doctoral school Build Nature at BOKU, which covers the whole range of construction. So the PhD will have access to an interdisciplinary team of supervisors as part of his or her advisory team. In addition, we could convince Diefenbacher Germany to also be part of the project, because they also never heard about using branches in their straining process. And with their decade-long experience, I think we can build on an industrial quality foundation. On the impact side, we identified 4 key sustainable development goals with sustainable cities and communities at the forefront. On top, on a regional level, we are confident that integrating branch wood into the wood value chain might increase the added value on a regional level as well. To achieve this, we identified 4 key research questions that we want to answer over the next 3 years. The goal here would be to create at least 3 scientific publications and multiple international conferences out of that. And with the aim to have the results accessible free of charge to the whole community, some of the funding will probably go towards open access fees as well. At the foundation, we want to investigate the technological potential of strands from branch wood compared to strands from stem wood. There's a reference. You heard Tobias talk about higher variability, different densities, some lower strength values, some comparable strength values. So we expect a similar variability on the strand level as well. And as we did already in storm hardwood, we want to try to explain this variability by the position of the branches within the tree, therefore giving the possibility to examine the wood quality already on the standing tree level in the future. Furthermore, we want to investigate different wood species, and we want to open up this field again to include some deciduous tree species, because 15% on the deciduous trees are still 15% that we could use immediately for structural products. Comparing this to pine as a reference in the strand-based products in Europe at least. The final research question regarding the structural application potential, where we want to investigate how does the branch-based, strand-based products, long word, fit into the existing realm of engineered wood products. To answer these clear research questions, we developed 3 nice little work packages for the PhD student to work through. First, the strand potential. So we will go back into the forest, cutting down some trees, gathering the branches and the stem wood as a reference, and transporting this material to the company Tiefenbacher, who will give us access to their technicum and create industry quality strands. With the strands, we want to investigate on a strand level the influence of the raw material, the processing conditions, and pretreatment on the resulting strand properties. That got a little mixed up. We expect a higher variability of these strands compared to the strands from the stem as well. As an example here, one important factor is the length of the strands in strand-based products, as slenderness drives performance as well. And we expect the branch strands to have higher variability in different length classes as well. At the end of this work package, we also expect a certain data set that can be used for modeling of this material, as we have an intermediary product described. With the remaining strands, we will create different panels at Open University using the same process or the same procedure that we developed for Unistrand. Therefore, we have a big data set to compare it to as well. And following mechanical as well as physical characterization. So the physical characterization will include thickness, swelling, and internal bond strength as key characteristics for engineered wood products, on top of tensile, compression, bending, and shear tests. The hypothesis here is if we take pine as a reference at different compaction ratios resulting in different densities, we expect that the strands and the panels from branch wood will sometimes perform better than the panels from stem wood, and probably also some will not reach the current benchmark. Last but not least, together with Tiefenbacher, we will decide on a range of density classes, coming back to the different strength classes again, and a range of mixtures. What do I mean by mixtures? We know from literature that mixing different wood species into one panel, we can offset the downside of another by a bit. And with these final tests, we will investigate the application potential. So if we take the existing realm of engineered wood products, we can currently identify a gap right around here, and we expect branch-up panels to lay right in that range as well. So we talked a lot about the scientific details of branch-up, the previous projects, and what we want to do in the next 3 years. To sum this up on one slide, we would say branches have technological potential. So let's branch up together and help to come from a burn to a build mentality for this undervalued resource. With that, we would like to say thank you. Oh, actually, we could spend 20 minutes on this slide alone, I guess. Yeah. So we would like to thank you, the Evergreen Prize, for initiating this prize and giving us the opportunity to present here. Furthermore, Boko University for providing us a workspace where we can follow our ideas as we like to. And of course, Professor Johannes Pommer for supervising the group, giving us the guidance to follow these ideas as well. The PhD students involved and also the master and bachelor students involved in the project. The list is not done here, I guess, or I hope at least we can add another PhD student with their. Thank you very much.
So, yes, please just shoot your questions.
One question, most of the wood-based materials or panels, especially the particle and strand-based materials, are without bark. So they have to be debarked as a round wood before they become a panel, because the bark is negative in gluing and in mechanical properties. And your branches are much smaller in diameter, and therefore the volume of bark is much higher, but it is much more difficult to debark the branches. Did you already consider a technology or the idea of how to get rid of the bark in your branches or with your branches before making the strands or whatever it is?
I mean, you investigated the bark content, maybe you can add something to this.
So you very well summarized the main problem with branches, so it's more complicated than standards, definitely. What we learned from company visits, for example, in Lansing, so they are very high demand of hardwoods, and they use beech, for example. But they know, they also told us they had some trials with smaller dimensions. It's a rotary drum debarker, but it just takes long. It takes longer. From a technological point of view, it's supposed to work. But in our work so far, we didn't look into debarking specifically, so it was really done by hand, motivated master students again. And of course, it works better if it's fresh wood. It depends also on the species. So poplar was very easy, for example.
But you already debarked before you made your specimens.
Yes. For the macrofibers, actually, we also used the poplar, for example, directly with the bark because it was fresh. And the first round was debarking, and then we continued with using the macrofibers.
Thank you.
Just had a question. I think it's a wonderful opportunity to obviously explore better wood utilization. As you pointed out, there's a lot of wood that's left behind or is burned, and that's a big challenge for us. We need to get more of what we have. Has your partner Deacon Becker or yourselves explored sort of the practical reality of the cost of transporting branches and or tree tops or whatever it is that you're using to a site to make that cost effective? And I know you're looking at the science, but I also want to be able to get the product to the mill. I'm just curious if you've got any thoughts on that, because I think that's a non-technological hurdle.
Yeah.
Cost hurdle.
I mean, that's one of the reasons that we talked to Ethan about it before, because as they are building the mills and the factories, they have a holistic view on these conditions as well, not just one specific site. And they were talking about the issue that some of their partners and companies already have in getting enough resource right now already.
Yes.
So I think with an increasing resource demand, we will also get into the economic feasibility to do that. On top of that, if we consider current firewood that's transported some distances that we would consider too far as well already, so why not transport this to a site like this instead of, Home Depot, for example.
Fair enough.
So on the modeling guys, I want to ask this question. You mentioned that you can imagine a model which gives you the properties of a branch depending on the position in the tree. How would such a model look like? And what's the main differences between a horizontal branch and vertical?
So to answer the question for the last part of your question, it basically goes back to the growth pattern. So how wood is produced during seed growth, and a flat branch basically differs due to the presence or more likely presence of tension wood zones, so highly oriented zones having an additional layer on the cell wall level, and it's also described by eccentricity. So the pith of the bark branch is not directly in the middle, but out centered. And that basically leads to these main differences. Also higher heterogeneity again, in comparison to steep branches. Steep branches, which in our opinion do resemble more of a stem wood structure. So that's, let's say, in a few words, only the differences, but yeah, but depending on the region, again, depending on the growth angle itself, so it's very rough.
And which type of model could you imagine?
So regarding the model, I would say there is two sides to that. So the one would be that we created some basic correlations of branch angle and resulting material property on a defect-free wood sample. So this definitely needs to dive more into detail on the standing tree, and with forestry moving towards single tree management, I think we can get a nice basic correlation out of that. On the strand level, I would hope for your input if there is cooperation potentially.
Maybe just at the last sentence, for the publication, shows the linear regression, basically taking positional parameters into account to explain bending strength with a linear regression.
Thank you. Great presentation.
Yeah, I have a question about with all new products eventually introduced to the market, that's a bill of those. And branch-based material will have to go through this process. Have you thought about this? How challenging that would be?
So similar discussion as to the side thing is if we feed a new raw material in an existing stranding process, if we get the right density class according to the OSB standard, for example, there is no need for an additional classification and standard classification.
I have a question to the resin content, because you have very nice diagrams here on density and mechanical properties, and also on product yield and average modules, etc. So each wood-based panel has a resin content, glue them together, and the resin is much more expensive than the wood itself. I think 1 kilo wood is 10 to 20 euros, and the resin is 2 euros per kilogram. I don't have the current data, so it's a factor 10. What is about the resin content with the branch wood compared to, let's say, OSB or other equivalent boards?
So I would say one of the main things that it comes down to here is the wood species that we use. So current adhesives are optimized for pine or hawthorn and America, for example. So I guess here we will be in the same range as current products. And as we have on the last slide for the application potential, we can see these different mixtures also influence the adhesive content. So I think it comes more down to the wood species that we want to use and want to mix together, how much adhesive we actually need.
I think we're at 29.5 minutes. Any last questions from the jury? Yes, Andrea.
Very short, why so many species, and are you thinking that in 3 years you can actually get to the bottom of all of them?
So we defined this rather broad on purpose because in the last project we realized, okay, in the initial phase, when we decide on the different wood species, we also have to consider felling season. So depending on when we start the project, it might be that we not have access to all the wood species. And as usual for these projects, you start on a broader scale and scale it down after. So we at least hope to get on the strand potential for the selection of wood species. And then similar to the last projects and to other projects, we will do a selection based on both. 3 to 4 wood species would be feasible, I guess, instead of 8.
Very good. Thank you very much. Thank you, Max. Very good, very interesting first presentation. And with that, I would like to call on our team Mike.
In 2020, the MycoLab project was launched, led by Nazanin.
Sorry, I think I'm going to stop the presentation. It's still school now, yeah. Sorry for that.
In 2020, the MycoLab project was launched, led by Nazanin Saidi and her team under the chair of Sustainable Construction at KIT, Germany. Myco refers to mycelium, the root-like structure of fungi. Mycelium can grow on different types of treated and untreated wood waste and other types of biomass. After drying, it solidifies without the use of glue or synthetic binders. The research focuses on selecting fungal strains and adjusting raw materials, temperature, pressure, and processing time. The goal is to produce customized materials from insulation panels to structural boards, enabling circular and low-carbon construction, all without any synthetic binder. 100% bio-based, 100% circular. The resulting product target markets are currently dominated by MDF, particle board, and synthetic insulation such as expandable polystyrene. What was once discarded as waste now forms the foundation for new possibilities, shaping a future with less environmental impact and smarter resource use.
Very good.
Thank you.
So,
So that's what we do at MycoLab with lots of passion, lots of love, lots of power to transform the future of construction industry, regard waste as resource. Looking at the construction urbanization map, in 1950, only 30% of people were living in cities. Now, over 56% of people are living in urbanized areas, and this number is expected to increase further to 68% by 2050, with a global population of nearly 10 billion people. What does it mean for us, for our cities? It means we need to build more, build homes, build infrastructure, the entire built environment. But building takes resources, and the resources are limited. So how we are going to build more without placing more pressure on our planet, on our nature, more than what we have already done so far? If we continue managing the resources the way we do today, the way Germany does, we would need 3 planets, but fortunately or unfortunately, we only have 1. This means that we should value resources more than what we are already doing. Construction industry is probably the most material intensive and resource intensive industry. It shapes the world we are living in, but it does it at a great cost. First, we extract, we dig into the earth to pull out massive amounts of raw materials. Almost 50% of global extraction goes to construction industry, a very heavy start to almost linear process. And then we produce. All these materials are turned into something that we build our cities with. We build large, we build very fast, but without so much thinking of what comes next. We also produce a lot of waste. Construction industry generates mountains of discarded waste. Cement, metal, wood, they are usually thrown away or treated like they are endless. So in general, we extract, we produce, we waste, a one-way path that our planet or nature can't take it anymore. And it's not only about the material intensity of our product, of our construction industry, it's also about the emissions. Construction industry is producing almost 11 billion tons of greenhouse gases every year. And it's not only about the CO2 that we are hearing every day. There are other gases, thousands, 100 times more potent than CO2, like methane and also nitrous oxide. So it's not only a material crisis, I would say, it's a climate crisis. So what sort of future we want to build for ourselves, for the next generation to come? And that's our vision, to create a world where resources are valued, waste is minimized, and nature thrives for the next generation to come. To have such a beautiful world, what are the alternatives that we have? And we just take a look at wood waste as an example. Every year, million tons of wood waste are generated. In Europe alone, in 2020, almost 50 million tons of wood waste was generated. Almost 55% was burned for energy recovery, and only 46% were recovered to material, something like particle board. And of course, energy recovery is important, but material recovery should come first, because every gram we reuse, it's almost 2 grams of CO2 that we store, we keep in the material for the longer time. And that's what nature does always. Nature wastes nothing. Everything is recycled, is repurposed, and it's regenerated. And that's what we should do from now on. So what if we turn to a regenerative material which turns back to the earth, which is built in harmony with our planet, with our nature? So we can start with using waste more than what we do and bind them together without anything additional, just with the help of the nature. So in our experiment, we are exploring the ways of using regional, local wood waste and agricultural waste collected from sawmills, from furniture producers, from discarded pallets, and also the byproduct of agriculture industry like hemp and miscanthus, combining them with mycelium, the root network of mushroom, to create a regenerative bio-based material. So the core innovation lies in mycelium. It's not us, it's the nature who does the job. But why we are so much interested in that? Because it has this self-adhering property to the fetus life. It forms beautiful cross-link with the substrate, so it acts like a glue. It grows really fast, and as it's also using really low energy. So at the end, it turns waste into a material which is 100% bio-based and recyclable. So we have a local, low-cost, and low-carbon material. It's perfect for what we need for our future. But it's not only any type of mushrooms or fungi that we use. We are mainly focusing on wood decaying fungi. That's what we usually see when we walk into the forests. They are our ecosystem recycler or ecosystem engineer, and our main focus is on white rot fungi. They're digesting these tough plant fibers like lignin and cellulose through enzymatic pathway. Yes, if we look at this time lapse taken by us, not in the best professional way, we see how mycelium grows. It grows into the wood, around the wood, and it forms this 100% bio-based composite, which is safe, which is scalable. It's waste not burned to pollution, but it's turned to possibilities.
So thank you, Nas, for telling us about how we need mycelium-based materials and how we need materials actually made from mushrooms. Next, I'll be telling you more about the properties and also the production process of this material. So you can see over here, as you have seen in the video just now, when the fungi is added to the substrate, particle substrate, it actually grows and spreads very quickly. And that turns the substrate with the mycelium into a block piece of material over here. This is actually a very lightweight piece of lignocellulosic foam. And if you look in the microscope, this is actually what you see. There are little particles of vegetative substrate, whatever you use, including wood chips, of different shapes and sizes. And these are actually being bound together by a very thin web of thin fibers. We call this network of thin fibers the mycelium. And just a fun fact, your hair is about 50 microns thick, which is about half the length of the scale bar over here. Hope you can see it. Yeah. And you can see that our mycelium fibers are much thinner than the diameter of your head. And yet they are strong enough to actually bind every single thing together without any additional binders or adhesives. So that is actually pretty amazing by itself. And because there are no additional adhesives, our material is completely bio-based, recyclable, and circular. This diagram actually shows the circular life cycle of our mycelium materials. Furniture and construction made from wood will inevitably turn into wood waste after some years of use. And with some processing, we can easily grind them into smaller pieces, something like this, into this ground up substrate. And with this substrate, we actually can grow mycelium composites with them. And we can make these mycelium composites in many different kinds of things. For example, furnishings or panels for construction as well. And with that, at the end of life, we are able to recover that material and grow more mycelium on it and make them into mycelium materials again. And that will serve us for many more years to come. And let's say at the end of the life, we don't want to recover them. We can also degrade them naturally, and they go back into the forest, and they can be grown into trees to make more furniture again. So that is definitely very circular, and you can do that also with agricultural waste. You may be very curious, how is such an amazing material made? Well, here's a summary. Basically, we start with culturing and selecting the mycelium strain, something that we think actually works best. Then we seed the mycelium into the solid substrates that we want them to grow in. After that, we leave them to grow and fully colonize the substrate. When the substrate is ready, we fill them into these forms so that we can shape them in whichever way we want. After they are fully grown, we demold them and we dry them. So the mycelium-bound composites in its original form, we call them new wood 1. It is a very lightweight and strong foam, like what you see over here. It is very close to insulation materials used in buildings. And let's say we decide to densify the material. We can actually do that, and it turns into new wood 2. So this is a dense and strong version of mycelium-bound composites. It has very similar properties to engineered wood materials, such as medium density fiber boards and different kinds of particle boards. So it's definitely very applicable in different industries that are currently using these particle board materials right now. You may be quite curious, what are the properties? We have definitely conducted some testing on this material. And right now, we are looking to improve its mechanical properties, its sound absorption properties, for example. We have done a series of tests, including mechanical, sound absorption, heat transfer, as well as durability and aging tests on this material. So these graphs show compression test results from new wood 1. In this set of tests, we actually tried to use different substrates of different particle sizes, and we used a combination of them. What we found from this is that when we mix different substrates, it actually helps the mycelium grow better and denser, and that actually creates stronger materials. This is because the mixture of different substrates actually can help the mycelium grow due to the different types of nutrition for the mycelium within the substrate itself. That was very interesting. And with that, we were able to achieve compressive strengths of up to 2 megapascals for our best combination. We have also conducted some bending tests on new wood 1, and what we found was that we were able to add wood fibers into the material to reinforce our mycelium composite. That actually helps to make the mycelium composites stronger. The wood veneers will also help to reinforce new wood 2, which is the denser version of our material. And with this, we were able to achieve bending strength of more than 20 megapascals, and the material has elastic modulus of more than 6 gigapascals. So this actually draws quite close to the commercial products now available on the market. We have also conducted some preliminary fire testing, and what we found was that light material, the very low density material, actually is a very good insulator. This is because there are many air pockets in the material, and that actually helps to insulate the heat from the inside and from the other side of the material when we are doing the testing. We also found that it does not emit any harmful or toxic gases into the environment because it's completely natural. So you will not have that strange mixture of nitrous oxide and the other harmful gases that was mentioned by Nas just now. So we also compared the performance of new wood against other commercially available, functionally similar materials. So for new wood 1, we compared them with rock wool. And we found that it actually has very similar thermal conductivity and sound absorption properties as rock wool. So rock wool is a very common insulation material being used in building nowadays. And it is denser than rock wool, but the strength is that it is actually much stronger than rock wool. That gives it some kind of self-supporting and better structural stability kind of properties. We also compared new wood 2 with medium density fiber boards and particle boards. So what we found was that it does have very similar strength and density to these conventional building materials. And because of this, we are very confident that we are able to actually apply this to many different commercial applications that are currently using medium density fiber boards and particle boards. So when we talk about green materials, of course we have to actually think critically whether is it green or is it really actually good for the environment. So what we did was that we conducted some life cycle assessment on our material. What we did was that we modeled the material, the production process of our mycelium-bound composites into 3 different stages. And for each stage, we will calculate, model and calculate the inputs and the products from each stage. The three different stages can be summarized as follows: the growth and culture stage, the incubation and inoculation, and then the processing stage for the final products. So with the model that we were using, the system boundaries that we were using, these are the results of our life cycle impact assessment. From here, it is pretty obvious that our new wood, labeled as mycelium over here, has the lowest environmental impact out of these different insulation materials commonly used nowadays. It has 6 times less climate change potential than extruded polystyrene, and 10 times less fossil energy demand than raw wood. So I think that is pretty impressive. Also, to add on, this is just the analysis for the production process. We have not done a complete life cycle for the other processes, such as the use and the end of life. And because of the circularity of our material, we believe that will actually make our material even better if we do a complete analysis. So we find that it is actually extremely important to continue further studies on mycelium-based composites and other green materials similar to mycelium-based composites, so that we can actually build and develop sustainably in a way that is good for the environment. And with that, Nas will show you some real-life demonstration projects that we've completed in the past.
Microtree is our first prototype. It was exhibited in Seoul Biennale of Architecture in 2017. It's basically the first larger-scale demonstrator showing the structural performance of lightweight mycelium materials. With parametric design, we were able to make our lightweight material load-bearing, so they were able to take their own weight, plus the weight of bamboo on top of it. This exhibition piece was there for 6 months, and after that it was composted on site. A perfect example of recyclability. And we have also made a smaller version of this microtree, and is traveling the world in different museums and exhibitions that we are almost losing track of where it is. We have also used our mycelium for other symbolic projects, not only about construction, but also about art and understanding the future. We made a beautiful human body from mycelium. It's a symbolic project of how we as humans can help our diseased forests or diseased lands with the help of fungi, with the help of nature. We also used mycelium in some beautiful furniture pieces like what you have seen in the video. We are also working in a collaborative project where we are mainly focusing on using lightweight mycelium as acoustic panels for interior wall fittings, for interior offices, and with the help of our partners, we are also reinforcing mycelium with a 3D printed wood system. This would help to improve the mechanical and acoustic performance of the material. This is also one of my favorite prototypes. We use new wood, dense version of our new wood, as interior wall cladding of a self-sustainable house in Batam, Indonesia. So this is a perfect example that how we can bring local resources into life without needing imports and exports. So this shows how we can make our cities, especially in the developing part of the world, because we are only 20% of the population, but most of the population is living in developing regions. We have also used our lightweight mycelium in a roof kit project. It's a fully circular demonstrator house. In that case, we use mycelium as acoustic walls and also for some decorative elements and lampshades. And now with Singing, we are working on a very exciting project to build a one-to-one demonstrator. It's a room system that we are using in a combination of our lightweight material and our dense material. This is going to be used as a quiet room space for having conversation and telephones. It's also a perfect example of how we can bring circularity into our everyday life. And of course, no innovation happens in isolation. To bring regenerative material into fully scalable demonstrator systems, it's not just a great idea, it needs collaboration. Scientists, designers, engineers, and a lot of forward-thinking companies. And for that, we have been lucky to work with leading partners in academia and industry, all with the same mindset of working towards circularity. And it's not only about this amazing product that we can make, the economic value chain we can create, it's also about the impact that we can make in line with sustainable development goals. And for me, this is a top priority. Working with only one medium-sized furniture producer in Germany, collecting their waste We can upcycle up to 15,000 tons of wood waste. We can save a lot of trees, save 1,000 tons of CO2, and also help the companies to reduce millions of dollars in waste disposal cost and carbon taxation. And this number would be a lot more if we think about it in a global scale. And for this special company, Chronic Neurat, we are also using their waste to produce a product for themselves, replacing the chairs that we are sitting on. We have a prototype that probably later in the evening we can show you.
Yes. And all this work is done only because we have our wonderful team, our wonderful multidisciplinary team from engineers to architects. And we believe that with our diverse backgrounds and expertise, we'll be able to push this project much further. But what we need to do is that we need to win the Evergreen Prize. With this money, we will be able to just expand our team, hopefully, and keep ourselves employed. We also need more lab equipment so that we can do more tests, we can get better results, and also definitely we hope to organize some outreach programs to better publicize this kind of wonderful materials, sustainable materials that actually help with the environment. So yeah, that's what we hope to do with the money that we get from this prize.
That we would like to thank you, dear jury members, the Evergreen Prize Stiftung, and also HST Group. We are here, and I think we are already winner. It doesn't matter who gets the prize, but everyone here is a winner. And I believe only together we can make a change. We can rewrite the story of our planet, of forest, and that is the top priority for all of us. Thank you.
I have many questions, but I put only one here.
No problem.
You focus on indoor applications, yeah? But even in indoor application, you need a certain amount of moisture resistant and water resistance. And you didn't mention this in your presentation. What is about this, let's say, moisture? You have high humidity, maybe in a room and something. How is the behavior and the response of the material?
Sure. So mycelium itself by nature is hydrophobic, but when it comes to a composite, it absorbs water because it has pores, especially the lightweight mycelium. So now we are working with some chemical industries to help us to develop coatings, biological coatings, mainly from made from, for example, the resins of produced by cactus and other plants. This would help us to seal our material better. That can help us improve our performance. We have done actually accelerated weathering tests. I have the slides here, but I can just explain it. So over 35 days of accelerated weathering tests in the super humid environment of tropics. We observe about 20 to 30% reduction of the performance over time. But this is something that we want to improve, and it's a research in progress, but it's a very valid question. This problem is less prominent in the dense panels because they are more resistant to wood for interior applications. For example, for the furniture producer that we are working with, they have already done in-house testings, and for them, it already passes the requirements. But of course, we need to make it better.
Thank you.
I have a question about the mycelium, growing of mycelium. It requires a controlled environment, and then you've been able to do it in the lab. But when scaling the business, how do you see that?
Well, actually, so for growth of mycelium, it depends on the species. Yeah, like different species and will require different optimal environment. But what we notice with the strain that we have selected is that it grows well in general indoors environment around this region, like in Germany in the lab. We don't use any additional heating. We just grow it in the lab environment with the normal room temperature and atmospheric pressure and everything. And actually does grow well. So if let's say we have to scale up this project, definitely we can do it in any kind of workshop environment that is cleaner. Of course, we have to meet certain standards so that it doesn't get our material contaminated or we don't have any problems. There has to be some standards. But just the general environment, we don't have to spend too much effort in trying to maintain, like say, moisture or the temperature. It is quite forgiving in terms of the strain that we have selected.
Yeah. It's very resilient, like us.
Yes.
So you talk about waste wood, but usually when it's waste and it's also contaminated, and
Yes.
so did you work on the contaminated wood as well, like or like different preservatives, adhesives and so on,
Yes.
or only clean?
So this perfect example has all this lamination, pieces, plastic, sometimes a little bit of metal inside. We work with cleanable waste, like this. We also work with contaminated waste. It works perfectly on both of them. Because mycelium also generates enzymes like lactase, peroxidase, they are also breaking down plastics. So they can still be able to digest part of it a little bit. So it's perfect to use kind of treated food waste because that's where the problem is. And usually the industries, it's too costly for them to clean it before giving it to us. That's why we try to optimize our process to be able to work with both of them.
And I have a similar question. So you currently have used this with the furniture manufacturer. And so was that just sort of wood waste without any contaminants in it?
So we use mainly the wood waste that is there. We also use pallet waste. We also supplemented with a little bit of hemp. But without that, it also works. We only add the hemp because it makes the growing time a little bit faster. But we have also used other sources of wood waste, mainly from sawmills, like we use a lot of sawdust to supplement or to densify our material. So we have also basically used other type of woods.
So if you imagine a production facility and you're scaling it, what does that look like and what does that cost?
That would be a dream. So at the moment, we are working with mushroom farmers, existing mushroom farmers in Europe, and there are a lot of them. We have also worked before with one farm here in Austria. So they already have the facilities to produce mycelium in huge scale. They produce 200, 100, 1,000 pounds daily or weekly. So they can produce a lot. And for that, you don't need to invest a lot on building a farm. You can already take advantage of existing farms because they most of the time have a lot of space available based on the season. And what we do is only post-processing the material to what you have, so new wood or a lightweight mycelium. So in terms of the size, it's not huge size. We can, because mycelium also grows vertically, so it doesn't need light, so we can grow it in a smaller space, but in a big quantity. But of course, with the help from farm and existing facilities. So we tap on the resources from wood industry and also from mushroom farming industry, and just we bring it together. And we also do not add any glues or any resins.
A quick definition. Why did you choose a density of 800 for a dense wall? Is this already a sweet spot? Do you have any idea how the strength to weight ratio changes with decreasing or increasing density?
So for the dense panels like this one, we can also, this is probably the densest version that we have. We work from 600 kilogram per cubic meter up to 1,000 kilogram per cubic meter. So 800 is just the average that we have. In terms of, yes, when we densify it, the weight to strength ratio improves, but we cannot densify too much because over-pressurizing the mycelium materials would cause delamination. So we found the sweet spot more or less is about 800.
Do you know the tensile strength? What is mycelium fiber? Is any idea?
I hope I knew the exact answer, but it's not because when it's everything, it's becoming together. And it's like growing in one piece. We can't really know what is the density of mycelium and wood. So it would basically look like this. It's mycelium grows together with the wood, and we start with 1% of mycelium, but it basically occupies the whole space. But in terms of quantity, we don't really know exactly how much mycelium we have in the composite. This is something we have tried to do some chemical analysis, but it needs funding.
So 1 minute to go. Any last questions?
Yeah, I would ask the same question as I asked the first presentation. So the building material rules are existing. So eventually this product will be launched commercially. Obviously, challenges
This is a work in progress. That's why we are starting to focus on starting the furniture industry because it's an easier market to go inside. And at the moment, we are also working with architecture officers, with construction, with developers to work on demonstrator projects. So with that, we can test the material more, we can understand it better, and we can also get it certified. There is also an institute in Germany, it's called Nature Plus. So they are in charge of certifying bio-based green materials. So we are also working together with them to see how we can basically tackle this challenge. But I know it's very painful process. It takes time, but it should happen because we cannot continue like the way we do today. So we are here to make a change. Probably it has cost me all the gray hairs that I have covered, but I'm happy about it. I love what I'm doing.
Thank you very much. I think this is an excellent closing statement. And, so thank you very much, Team Maxwell. The next thing will be hyperlignification, and after we're going to make a 15-minute coffee break, so we need to stay focused for half an hour more. And then there's a little room
To protect wood from decay, impregnation with toxic biocides is often used, but biocides can harm the environment. To change that, Emil Tubring and his team at the University of Copenhagen developed a new method to protect wood. It is called hyperlignification, and it impregnates the wood structure with lignin. Hyperlignification was made possible by a breakthrough discovery. The team succeeded in dissolving lignin in high concentration in water-alcohol mixtures. Lignin is a main component of wood that helps trees resist fungal attack. Lignin is also a byproduct of the pulp and paper industry and is available in large quantities. Hyperlignification increases the wood mass by up to 90%. That's more than 10 times higher than previously achieved. The material shows greatly improved resistance to fungal decay and increased fire resistance.
Thank you all. Hi, my name is Emil, and this is Andrea, and we represent Team Hyperlignification, where we supercharge wood with lignin. But I want to start off with a story from back home from where I live. I live in an ordinary single-family house in a village outside of Copenhagen, Denmark. We have a garden, and in this garden we have a fire pit. You see it on the picture on the left. And 5 years ago, I wanted to build like a living fence around this fire pit. Since I'm passionate about wood, I wanted to make a structure out of wood. And I'm a wood researcher. I'm interested in durability of wood in outdoor environments. So I spent perhaps a little too much time searching for good materials, for durable wood materials that were good in ground contact. And I ended up settling on biocide treated wood because it was cheap and it's widely available. I can get it everywhere in the stores in the dimensions that I wanted. But I was really not happy about this choice. As a wood researcher, I know that biocides are bad for the environment, and I know that they over time will leach out and harm the environment. So this year, when we needed a new fence towards our neighbors, you see here on the picture on the right, we said no to biocide treated wood. We didn't want it. So instead, we ended up selecting durable tropical hardwoods. And we ended up having the fanciest and most expensive fence in the entire village where we live. That's a surprise. But this illustrates this dilemma we have as consumers. If we want wood, durable wood products for outdoor use, the choice is between something that's local wood, that's cheap, but also toxic. And if we want to go for non-toxic options, we have to go for non-local species
and quite expensive wood products. And this is actually a broader societal challenge because wood in construction is booming, and that means we also need more wood for outdoor use, durable wood products for outdoor use. And all existing solutions we have are suboptimal, with significant downsides to them. I mean, biocide impregnated wood is toxic, tropical wood is non-local, it's expensive, and it's sustainable, sometimes we're in doubt. Of course, we have modified wood products on the market, like chemically modified wood, which is high performance materials. But these are also based on non-local wood species, and they are quite expensive. And thermally modified wood is only semi-durable, and it's not good for ground contact. So we need new solutions for durable wood in outdoor environments. And around the time that I made this fence around living fence around our fire pit, there were some interesting things happening in our labs. Our team has for years worked on lignin. Lignin is a main component of wood, and it's also the component that protects the material from fungal decay by making the wood less attractive as food for fungi. I mean, many fungi would not even touch lignin. Lignin is also a large-scale byproduct from the paper industry that has so far been difficult to utilize because it's very heterogeneous and it's insoluble in water. But our team discovered a way to fully solubilize lignin, all of it, to make stable, highly concentrated solutions of lignin, up to 65% lignin, using just simple mixtures of water and alcohols. And these solutions were initially intended for use as fuels, but we thought, hey, since lignin has so interesting properties when it comes to protecting wood from fungal attack, could we perhaps add more lignin to wood and then gain more of these protective qualities of lignin? And that's why we called upon Andrea to help us out, see if these novel lignin solutions were any good. Could we impregnate wood with them?
Thanks, Nick. And yes, we did. We tried and we impregnated wood with lignin solutions, and the results were unbelievable. So the numbers, the feeling, the color. We have been working with modified wood for years, but we have never seen something like that before. But how did we do it? It was quite straightforward and simple because we used vacuum impregnation. Then we released the vacuum, soaked overnight at 50 degrees, and then dried the samples. After drying, we leached for a week to simulate like outdoor weathering, and then dried again. So this is what we got at the end, and it really felt like deep penetration, and we call this hyperliquefied wood. But how much lignin did we squeeze into the wood? A lot. So the mass gain was also very surprising and unbelievable at first glance. So we reached almost double the weight in some species. We tested this hyperlignification across several species, broadleaf conifers, and even after leaching, the lignin sticked into the wood. So then we wanted to know how this would affect the properties. And one of the key properties we wanted to address was hygroscopicity. So we use water contact angle, and we expose the cross section, so which is the section that most readily absorbs water of our samples, both untreated and hyperlignified wood. And we saw that these droplets that we were dropping on the surface were being readily absorbed by the untreated samples up to 1 to 2 seconds. While for the hyperlignified wood, it takes minutes to absorb, so the energy of the surface is lower, so higher quantity. Then we took it a step further, and we want to address the durability. How does this wood behave against fungal attack? It was our main question to address. So we set up a fungal decay experiment, and we used one very aggressive fungi that we tested in our lab before, which is Formitopsis pinicola brown rot, and we exposed the sample to this brown rot for over 10 weeks. What we see here is hyperliquefied wood after 10 weeks, and actually the fungi could overgrow the samples, which is an indication that is non-toxic actually. The hyphae could grow around the wood. But when we looked into the mass retain or the mass loss in hyperliquefied wood across all the species that we tried, the wood was barely untouched. While for the untreated samples, there was huge mass losses after 10 weeks. How did these work so well? So we literally zoomed in, we took microsections and used a stain, which is safranino, which targets lignin substructures and make it look purple under our eyes. And what we saw here is that it was quite revealing because we could see that the lignin impregnates the voids, which are the large vessels and the small ones of the fibers. So the lumen of the fibers and the vessels were impregnated. But not only that, if we zoomed in, we could see there is a darkening around the cell wall, which meaning that this penetration is not just the surface or like or blocking. So we are modifying the structure, and we think that this is the key actually for the long-term durability to see. But so lignin is very not homogeneous out there. So there's lots of types. Do they all work? So we tested several of them and we figured that actually the one that works best are the one that are less water soluble because the other don't stick very well to wood. Luckily, like craft lignin here is one of the main ways that stream from pulping and paper company. So what we are actually using is the one that we are most readily available in the market. And then we wanted to test fire retardancy, and we saw that with microcombustion calorimetry, the initial heat release was reduced when we burned hyperliquefied wood, while the char pyrolysis peak moved to higher temperatures, meaning that not only we improved the fungal decay resistance, but here we are seeing an improvement in fire retardancy of the wood. So then we kept asking ourselves, we were kind of playing devil advocates, why is this working so well? What is the reason why we are obtaining 90% mass gain, which is kind of 10 times larger than previous experiments in other labs? So the reason here seems to be that lies in the concentration of lignin that we can put into our solutions. So since we have been able to develop this solution with high concentration in lignin, we can obtain very high mass gains. And then we took 2 steps forward, and we, like in both attempts, tried to upscale these and went to an industrial facility and asked ourselves if we could actually now just plug and play these into an existing facility. So we brought our small samples, but also larger samples, and in a pilot scale industrial facility, parking pressure, temperature, 50 degrees, so nothing fancy there. And what we saw is that though we got unsatisfying mass gain in some cases in larger samples, lower than in small scale, the key point here was that we actually were able to use these in a facility without changing parameters, without making big modification, no safety hazard also. So very excited about this. We came back to lab, we were like, okay, now we need to improve this impregnation in larger scale, but we need a lab to do so. So we developed a larger vessel for impregnation of larger samples, longer samples. And yeah, this is what we're doing at the moment. And we see that our aim is to reach the mass gain that we saw in small scale, and we're not too far from there. And for example, with each sample, we even like have higher mass gains than the smaller samples. Yes.
Yeah, and you have samples in front of you in the jury. So clearly, there's more to do. There's more to explore because hyperliquefaction with liquid solutions is such a new research topic. So in the next step, we want to focus on some of the fundamentals, like the effect of lignin size and lignin chemistry, and how these lignin solutions are transported in the wood anatomy and how they interact with the material. So let's take the first one first, the effect of lignin size and lignin chemistry. I know this is a busy slide, but please bear with me. In order to investigate this, we want to try to reduce how heterogeneous lignin is when you get it from the paper industry. Because when you get it from the paper industry, it's a zoo of lignin molecules of different sizes and chemistries. So we want to use solvent fractionation, which is a method that utilizes that the solubility of lignin molecules in a specific solvent depends on the size of the chemistry. So by having different solvents and using them sequentially, we can actually split up this initial broad size distribution, this initial soup we have, we split it up into different lignin fractions that are more well defined with a more narrow size distribution, and make these fractionated lignin solutions. And try to use these to better understand what's actually going on during hybridification. And we did it once actually, where we just split up this paper lignin into two like small molecules, large molecules. And what we saw was interesting because the small molecules, we penetrated the cell walls, but did not fill up any lumina. Whereas the large molecules only filled up the lumina, but did not penetrate the cell. So we have these two different effects that Andrea was talking about, where you fortify the cell walls as well as provide a physical barrier to fungi in the pore structure. We want to go further down this route and study how more well-defined fractionated lignin solutions are transported in the wood structure and how lignin molecules are migrating into the cell walls. We want, like with regards to the fluid transport, we plan to use X-ray tomography. When it comes to understanding and seeing this penetration of cell walls, we are using confocal laser scanning microscopy or similar techniques. And this interaction, we want to use spectroscopic techniques to see how the fluid and the cell wall, how they interact using spectroscopic techniques like low-field NMR. And basically, we want to better understand how these solutions behave in order to make even high lignification work even better. But boy, what a ride it's been since our team first discovered these how to make these highly concentrated lignin solutions. And then when we started to impregnate and highly lignify wood, we've just seen a booming interest from industry stakeholders. So now in our work, we actually follow two tracks. We have a research track where we try to better understand how these lignin solutions behave inside the wood. And we have an innovation track that goes more towards technological development and upscaling towards eventually launching a spin-out company in the near future. And the reason we can push forward in multiple tracks is because we have quite a broad and strong team with different expertises involved. I myself, I come from civil engineering and wood science. Andrea has a background in nanoscience, but we are luckily surrounded by specialists and experts in biorefining, biotech engineering, lignin chemistry, and as well as very skilled lab technicians. And with regard to the innovation track, we have an industrial advisor as well as a business advisor involved. So we feel quite confident that we can push forward both in terms of the science and the technological development. And we believe that hybridification has potential massive impact. Because the situation today in Europe is that the paper industry produces 11 million tons of lignin every year that's been incinerated in the paper mills, whereby the carbon from the lignin is released to the atmosphere as CO2. At the same time, in Europe, we're producing 6.5 million cubic meters of biocide impregnated wood every year. And we would like to change that. So, with hyperlignification, if we use 15% of the available lignin in Europe every year, 15%, we can replace all biocide treated wood in Europe. Hereby avoiding using 120,000 tons of biocides every year as well as avoiding releasing millions of tons of CO2 from not burning the lignin in the paper mills, but instead taking it and embedding it in the wood by impregnation, supercharging the material with biogenic carbon that is kept in the lignin. So there's plenty of lignin to actually do this. And we'll end up with this hyperlignified durable wood product where we have both the carbon from the wood itself as well as the added carbon from the lignin. So hopefully, next time I have a construction project at home, I'll be able to choose a hyperlignified wood product that is highly durable, it's made from local wood, it's non-toxic, and affordable. That is the vision that we have. Thank you so much.
Thank you for the presentation and the ideas. You had one of the slides where you showed the smaller are the samples, the more you have mass gain. And this tells me that most of the impregnation pathway goes longitudinal. Yeah? And if you have the upscaling process in the final products, you need radial and tangential pathways to impregnate the material, which is for me the most crucial part now. How do you think you will achieve this? The separation is one thing to make some fractions a little bit smaller, but you always have the phenolic compound in there. Huh?
Yes, you're right. But these super molecules, if you reduce the average size of the lignin molecules, you also decreases the viscosity. So there's also viscosity component here.
Okay.
So we are trying out a lot of different formulations in terms of like what's the solvent system, how can we improve the penetration by both looking at the lignin molecules as well as the solvent system itself in order to achieve good penetration. And this is unfractionated lignin, like the samples you have in front of you, like there's the beach, I think, where you have 40% mass gain in these small samples and actually get quite a good penetration. We can see also in the other direction. It's not perfect. We're not there yet, but we have good ideas how to move forward. And I would just like to point out 40% mass gain in the beach. Now we're in a range of densities around 900 kilos per cubic meter. So we are close to like durable tropical arguments. But of course you're right. It's something that we are continuously doing. Very good.
I love that all of the presentations so far have really focused on sustainability and getting more or less or utilizing in this instance a product lignin that's burned. I did have sort of two questions. I think they're probably easy to answer, but I was really confused as to why you chose tropical wood. Like in Canada, we use cedar, we use pine, we use local wood for outdoor things, for outdoor products. So I just didn't understand why you tried it for tropical. And then the other question, which has to go with when you talked about tropical, you said expensive, exactly, right? And question of sustainability, but you ended your presentation saying affordable. And so I think the affordable probably becomes a little bit better with local wood, but also I want to understand the affordability of the process and people's willingness to pay more. So why tropical and talk about affordability?
It was also again a question of what we could get. Like you're talking about my family and
yes.
our family.
Yes.
But it was a matter of like what was available in terms of durable wood products. That's why we ended up choosing these products. It's not about what's available in the market. But when I say affordable in the end, like the calculations we're doing right now, in terms also towards moving towards upscaling and business, is we aim for a price that's around that competes with thermal wood. So it's more expensive than biotech wood for sure. But perhaps that's the price also coming down, but factor of 2 perhaps. But biotech wood is also super cheap.
Yes.
It's really cheap to be unfriendly to the environment.
Exactly.
But we're nowhere near like Japanese according these very high performance modified wood products. We definitely perfect.
Okay, so affordable relative then, perfect.
Yeah,
Thank
exactly,
you.
yeah, exactly.
Excellent.
Thank you for the presentation, and so I have a question. If you have been looking at the dimensional stability of how it is impacting it, is one question, and the other, and when you were showing the stability properties, in majority of the cases, sooner or later, evolved. And so if you have been looking into also how to actually use it beyond just a solid block.
We haven't looked at the bonding, because initially we tried to compete with biotech goods, which is poles, railway sleepers, whatever weight that you make and then use. But it's a really good point in terms of what about bonding. And the second, the dimensional stability, yeah, we actually didn't try it yet. It's in the planning. But what we expect is that since some of these molecules penetrate the cell wall, they also mean we have like this bulking effect of the cell wall, meaning that there's less space for water, so we expect it to swell less, to be more dimensionally stable. And that's also a reason why we expect it to be very durable, is that it's also more dry. The wood is more dry compared to other, a bit like other modified wood, where you exclude water from the cell wall. And hereby create more stable material that's also less attractive for fungi to.
Sorry,
Yes.
we could see that when we're doing water contact angle, the weight absorbs is quite different because it looks like the lignin blocking pores also in the other direction, not only on this region. It confines the absorption of water to the spot in which the droplet goes. And then, of course, in this case, it's 2 minutes to absorb it, but we can see that it's more confined. It looks like the bulking of also the spreading of the moisture within the structure.
Very interesting. Do you know how the mechanical properties change with increasing the content? You have pre-developed
We have some measurements to look at the mechanical properties. What we initially wanted was not to deteriorate, like thermally modified wood where the properties deteriorate. So the benchmark was just like, let's not make it worse. And it seems that it's not worse than the test that we've conducted so far. The surface hardness is actually increasing, which is also interesting when it comes to durability against termites and marine organisms, where it's not so much the moisture availability that's the question, but more like the surface hardness when you have these jaws or whatever that choose material. So I'm not necessarily sure that we're improving the mechanical properties, other than a drier material has better mechanical properties. So having a drier cell wall would mean that we expect that mechanical properties to be better, say, under similar climatic conditions.
Do you think that it could be sufficient to really increase the surface volume?
Yeah, we are thinking about that because we are thinking about different targets depending on the usage. If you think about creosote impregnated wood, it doesn't go throughout the whole railway sleepers that they're climbing on. You just need like a coating of a few millimeters or several millimeters or throughout the whole sample. So yeah.
Yes, to supplement. So it depends on the application. Are we talking decking? Are we talking in-ground contact, marine structures, facades? They can have the different applications can have different minimum retention that's needed. And of course, we don't want to overdo it just because we can. So in terms, yeah. So we're also trying to diversify, looking at the market. Where can we first go to market? Where can we first introduce this?
And where can you go first?
Yeah, perhaps like out of ground contact would be an obvious like, to try out. We're looking at playgrounds right now as a way of easy testing where the whole building is not falling down, like an or urban furniture, like outside furniture.
Yeah, maybe last question. The existing wood industry, thermal wood, is very established. We have very, we are thinking about how to penetrate this market and how to make it a commercial success. I mean, because the capex part is significant. So how do you see yourself there?
We don't intend to build an impregnating facility. We want to make the fluid and sell the fluid to impregnating facilities at first. And we're collaborating actually with some larger companies. But you see, on the longer term, we'd also like to include this technology in the paper industry. Like so a lot of these larger firms both have paper mills and sawmills and also impregnating facilities. And we can close the resource loop. So they have the raw material, the liquid production, they can just move it to the impregnating facility and use it. So those are the two commercial models. First, buying liquid, making solutions, selling it to the impregnating facility.
Thank you very much.
Thank you very much.
As promised, we are going to take a short 15-minute coffee break. This means we are going to commence at 10:55 in the second 15 minutes. Thank you. So we are ready to proceed with the final two presentations this morning. I think I would like to welcome to the stage Jörn Rand and the team from KDH Stockholm.
Wood is typically opaque, but after a process developed by Wanwan Lee and her team in Stockholm, it becomes transparent and can even harvest sunlight. The modification involves several steps. First, lignin is removed from the wood cells. Then the wood fibers are fibrillated at the nanoscale. The treated wood is further infiltrated with transparent polymer and functional particles, for example, luminescent quantum dots, enabling light concentrating, conversing, and guiding for electricity generation. One potential application is in window systems. They aim to make a material where over 80% of the visible light passes. The UV light and partial visible light are converted and guided towards the window frame, where it can be collected by solar cells. The project combines renewable materials with clean energy conversion. Wanwan Lee has over 10 years of experience in transparent wood research. Together with her team, she is advancing the technology further.
So thanks for the nice opportunity for us to present our idea and the project here. We are a team from KDH working on transparent wood-based luminescent solar concentrator towards zero energy buildings. My name is Yuan Li, and associate professor at KDH. This is my colleague, Jing, a PhD in Monroe. In addition to us, we also have 5 more members in our group working on transparent wood, focusing on transparent wood scalable production, properties tailoring, and properties understanding and the devices assembly. So this is the division photo that I'm reading right now. So transparent wood is optically transparent polymer-filled wood composite. Our long-term vision about transparent wood and this project is to replace glass, like the windows, in buildings with our transparent wood. And we want to shift the normal concept of glass in windows to the energy positive buildings or energy positive windows in buildings by integrating energy harvesting devices, and then achieve this ambitious goal of zero energy and zero emission buildings in the future. So why zero energy, zero emission buildings, and why we want to replace glass? So here are some facts about buildings that we have to admit. So first, building sectors have over 30% of global energy consumption and greenhouse gas emission. So based on this, EU now has set a new requirement. All new buildings must be zero emission by 2030. And now with the increasing buildings, and the buildings structures also changed. For example, the wall-to-roof ratio is increasing, and the window-to-wall ratio is also increasing. That means we have a lot of glasses in the buildings, in the trend. And glass is the main material for the windows, but it has a lot of carbon dioxide emission. Estimated one here is around 9 million tons per year. And this means a lot of the carbon dioxide emission. And In addition to this, the glass market is continuously growing, and the projected market size for glass is approximately US dollars 1,675 billion by 2030. So that's why if we would want to have the zero energy, zero emission buildings, we need to have sustainable and energy efficient materials. So in this case, transparent wood shows great potential. The reason is that it is optically transparent with could be up to 90% optical transmittance, potentially could replace glass. The second is that transparent wood is lightweight, around 1.2 gram per cubic centimeter density, and for glass, normally over 2. And transparent wood is strong, can be used as a construction materials. In addition, transparent wood has low thermal conductivity, which is around 1/5 of that of glass. So that means during the building usage phase, the energy loss will be much lower if we have transparent wood windows. And then transparent wood potentially have a lower carbon footprint because glass is processed in a really high temperature, around 1,600 degrees, and a lot of the carbon dioxide emission is due to this transportation phase. And the transparent wood has lower processing temperature and has lower density, so potentially could have lower carbon footprint. In addition, transparent wood market is still new with great potential. The estimated market size for 2024 is 260 million. This will grow with annual growth rates around 7% from 2024 to 2030. This is the projected growth rate. So transparent wood has a really great potential market. By combining this luminescent solar concentrator into the transparent wood, we want to give transparent wood more functionalities. For example, to harvest the solar energy. This is one video that shows this luminescent solar concentrator concept in glass. So when the sunlight irradiates on the glass, this one, the light partially will be transmitted, the visible light, and the UV light could be converted to IR, and also the IR goes to the glass, will also be guided through the total internal reflectance to the edges of the glass. And then when you could attach the solar cell and in fact generate electricity from the device. So our concept is to replace this glass with our luminescent transparent wood. And with this concept, we could balance both the energy harvesting and these aesthetic views. So that is our strategy. Transparent wood-based luminescent solar concentrator. Our goal here is to get luminescent transparent wood with transmittance over 80% and haze less than 20%, wood content over 30%, and the quantum yield of this luminescent transparent wood over 30%. Why we want to have a high transmittance? Because we want to get this aesthetic view of the window. So we want to have higher transmittance and also want to get more light. And then the haze is lower because if you have high haze, you will have a high light loss during the propagation from your face to the edge. So we need to have low haze for this device. And wood content over 30% try to further enhance the sustainability of this material. And quantum yield currently is low, for transparent wood composite, less than 40%. So we want to further enhance the quantum yield to further enhance the light use efficiency for the device. So this is the current state of the art. So first, the transparent wood currently have high haze, typically 80 to 90%, and we could achieve around 55% now. But for this luminescent solar concentrator device, we need to further decrease. This is a radically change from the field of transparent wood. And this we need the understanding, the fundamental understanding of the light interaction with transparent wood. So we previously already know that the high haze is mainly from the refractive index mismatch between the infiltrating polymer and the wood scaffold. The second is the interface debonding during the polymer curing process generated. Another one that is normally neglected, and we found recently is really critical for the high haze, is the non-cellulose aggregation in the cell wall. So our goal is to further decrease the nanocellulose aggregation in the cell wall. From previously native wood could be up to 100 nanometers, we want to decrease less than 20 nanometers. So this is also the focus of this project. And then the second, the quantum yield of a transparent wood, normally less than 40%. And from this project, we want to achieve a high quantum yield with a value over 50%. By combining the achievement of a low haze and high quantum yield, we want to enhance the power conversion efficiency for this device. And here shows one reason why normally the luminescent transparent wood has low quantum yield, because when we infiltrate quantum dots inside, normally it's really easy to get aggregation of quantum dots, which have the quenching effect, leading to the lower quantum yield. So next, my colleague Juqing will tell the details of how.
Thanks for the introduction of the background from Yuan. Well, next I will introduce the detailed approaches to fabricate the transparent wood-based luminescent solar concentrator. We plan to solve the issues in steps. The first step is to fabricate a clear transparent wood and with low haze. Well, normally we produce a transparent wood just with the unification, and after that we do the polymer infiltration. But here we add a step with that is in situ nano defibrillation. It is used to reduce the aggregation of the nanocellulose inside the cell wall, and it can help us to assist the polymer infiltration and to get a more homogeneous wood-based materials. And this can help us to reduce optical heterogeneity and the interface debonding, this problem that we have mentioned before. And after that, the densification are also added to improve the wood content inside the structure for best sustainability. And the second step is to fabricate high quantum yield luminescent so transparent wood. Normally we think that the quantum dots are all hydrophobic, and there will be a heavy quantum dot aggregation inside the luminescent transparent wood. So we think the wood templates should also be hydrophobized to improve the compatibility between the polymers and the quantum dots and also the wood template. And after that, we do the densification and the polymer infiltration, and we can get a high performance luminescent transparent wood. And the third step is the device assembly. We attach the solar cell to the edges of the transparent wood, and it can convert the solar energy that has been wave-guided to the edges and to the electricity. And here are the project plan we designed. The first step, the first work package is that to fabrication of the clear transparent wood. It will start from month 1 until the month 24. And the work package 1 can include the scalable gamification and the in situ nano-defibrillation, controlled gasification, and the polymer infiltration and cooling. Well, among them, the focus is the in situ nano-defibrillation, and it will cost almost 2 years. And after that, the work package 2, the fabrication of the luminescent transparent wood, will start almost from month 7 to month 30. And it will include the wood template defibrillation and the quantum dot infiltration, and also the polymer infiltration. And the first one and the second one is equally important for this step. And after this, the work package 3 is the device assembly. In this step, the characterization from the materials from work package 1 and work package 2, and also the characterization of the device about the photovoltaic should be tested during this step from the month 7 to the end of the project. And during all the project running, we will do the examination for about the project results and about the activities. And about our competencies in our group. First, I will include the 10 years of experience of the transparent wood fabrication and the understanding of the properties and mechanicals. This can provide our deep background to push this project. And the second one is that we have a big team with diverse expertise, including the material science, optics, and photonics, and molecular modeling. And third one is that we have a long-term active collaborator, the Professor Ilya Sekchkov. He is professor in the nanophotonics and the nanofabrication, and he has a lot of experience in the luminescent solar concentrator. He will support us with the device assembly and also help us to have a deep understanding of the interactions between the transparent wood and the light. And furthermore, we have a lot of access to the great infrastructures at KTH and also at many different affiliated organizations, including the Wallenberg Wood Science Center, the Wallenberg Initiative Material Science for Sustainability, and also from Digital Futures and Research. We believe that our team is excellent and ready to push this project to success. Well, that's all. Thanks for your attention.
Thank you for a nice presentation. And since you were listening about lignin, I wonder what do you do in your case? And the second question, if it burns the transparency.
So first, we have two strategies regarding lignin. The first shows here, we do the lignification because lignin has a large refractive index difference between the cellulose and hand-cellulose, which will influence the optical properties. So that is one step. We also have another strategy, try to keep lignin inside, only remove the chromophores. You could still use lignin to keep the mechanical integrity of the template for easy handling and processing. So that's the question regarding lignin. And the second, burning, that's a really nice question. That's we are also working on is the fire retardancy properties and transparent woods. Currently, we are having two strategies. One is to infiltrate the polymers with fire retardancy properties, so to enhance the fire retardancy property of the final product. The other is to coat the transparent wood with nanometer safe transparent fire retardancy coatings to protect our product. Thank you.
I have a question. You have these nice sketches here about the samples. What is about the size of the samples you are currently working on? Because in long term, you must get bigger fields, with a huge bigger area. What is the current state of your let's say, films or gases?
That's a really nice question. Everybody wants to know that.
Yeah.
So we're in the lab scale, and basically the construction of the lab facilities, we can now working on the 20 centimeter by 20 centimeter piece. That's the largest one we can work on. But it should be easy to scale up in industries since the processing, this can be directly used the pre-preg processing in industries. So it could be easily to get larger piece.
Additional question, is this spruce or softwood what you are using?
We worked both softwood and hardwood. We worked on pine, spruce, birch, balsa, aspen, ash, we all tested.
I just have a question. You mentioned haze is a challenge, obviously, in order to have the solar benefits. So you said typically, right now, there's 80 to 90% haze. You've got it down to 55%. You want to get it down to 20%.
Yes.
Is that what the prize money is going to be used for? What is your intention if you were to win the prize money?
So that is the key part to get this clear transparent wood. Since now we can already assemble the device, and the light use efficiency is not that good enough. But if we could radically change the haze from level like 55 to 20, we could further significantly enhance the light use efficiency.
And how do you plan to do that?
So the plan is to do the cell wall nano defibrillation. That is the reason we noticed really critical for the high haze of the transparent wood. This previously we already noticed the contribution from refractive index mismatch and the debunkings, but neglect this cell wall inside the fibrillation application.
And is that what the 300,000 euro prize money would be used for?
That is the key part. The second part will be the quantum dots, the nanoparticles infiltration into the cell wall, uniformly distribution. That is also a key. Yeah.
Okay, thank you.
Thank you for the presentation. Which types of polymers do you use and are they biodegradable?
Oh, that's good question. Currently, we mainly focus on MMA, but we are also working now on polymer that is fully bio-based. But if we aim for windows, we don't want it to be degraded really easily. Yes.
Do you have any experience with aging in yellowing of surfaces?
If you're under really high intense UV, after a long time, we could see a little bit yellowing. But generally, the pieces we prepared like 2 years ago is still okay in the
Yeah, thank you for the presentation. I'm thinking 2-3 steps ahead here. The existing plastic cells glass manufacturers very established in the industrial processing methods, supply chains, how are they controlled? How do you see market entry for the product? Do you see this being adopted by the glass manufacturer or by the timber industry in competing?
So our goal is to compete with glass. But if we start from the easy step, it will be more from the composite industries using pre-preg, using our like wood industry materials and combined with composite processing industry facilities, and we could easily get large products and promising products out. And finally, we want to compete with glass. But at least now we already done our own calculations. We could already compete with polymer-based structures. That's no problem now. It's the further step to compete with glass industries that already established for many years.
I didn't quite understand, or can you explain it in a short version? You have the light, the sunlight comes in to the glass, and then you have some deviation, as you said, you have the UV light, and the UV gets to the infrared and goes to the edges. What is the physical process? I didn't understand this deviation of the radiation. Is it a composite or is it a nanofibrils, or what does it?
Yes.
What is behind that physically?
So first is the spectrum of solar energy.
Yeah.
Is from UV to IR. We want to fully use the spectrum. We want to have a perfect visible transmittance from 400 nanometer to 800 nanometer. Yeah. That's the target over 80%. Mm-hmm. And then the UV part, we want to convert the UV light to IR part. Mm-hmm. And then the IR part is easily using the total internal reflectance, that when the light shining on the glass, it will be guided to the edges.
And how is this?
Here is here is the feature of the wood. Wood, we have this preferred alignment of fibers. The fibrous aligned. They have weave guiding in
okay,
that.
now I understand. Yeah. Okay, perfect.
Yeah,
Thank you.
I should explain. Yeah.
Any more questions from the jury? If not, I have a question. I'm breaking my own rules now. Right? I'm not a professor and I'm not so science. But what is a quantum dot?
So it's the nanoparticles that they could emit light when you shine. Normally, we can transfer that light energy, for example, from the high energy wavelengths UV, that they could transfer to the low energy wavelengths. And then they emit the light. But that is normally less than 5 nanometer particles. Carbon quantum dots, silicon quantum dots.
I have one more question. You're investigating, your project is very clear what you're doing, but there could be some other things that would come out. This product, which is very strong, transparent. Are you open to seeing other spin-offs from your research?
Yes, we have a student, colleagues, he's not really student now, he's a researcher now, is preparing for the startups. Of course, we also need to apply extra funding to support us for the spin-off. We're already getting connection with the KDH Innovation to start the steps now. And the good thing for this processing is not constrained only to wood, but also could be applied or transferred to other cellulose materials treatments for more products based on cellulosic resources.
Very good. In this case, thank you very much for the presentation.
Thank you.
All right, so we are going to switch from ATH to ETH. Stockholm to Zurich. Team Lignovolt, please come on stage. The final presentation for today.
In 2020, the MicroLab project was launched, led by Nazanin Saadi and her team under the chair of Sustainable Construction.
Switch to fungi
At 8AH and IMPA, the Lignovolt team is developing a new method to generate electricity from motion using wood and the piezoelectric effect. Piezoelectric materials generate electricity when they are pressed. This useful phenomenon is widely used in electronics. but they often rely on lead-based ceramics, which are environmentally harmful. Lignovolt presents a bio-based alternative. The researchers embed Rochelle salt, a natural byproduct of wine production, into wood. The process begins with laser cutting cavities into the wood. These are filled with Rochelle salt, which acts as the piezoelectric generator. Next, a bio-based ink is applied to the surface. Laser treatment converts this layer into a functional carbon electrode. The resulting structure, a wood piezoelectric composite, is sealed with protective bio-based coatings. First prototypes include sensing and energy harvesting floors. The system offers comparable performance with a 60% lower carbon footprint than conventional materials.
Nicolas, du stehst vor der Kamera.
Thanks for inviting us to this very great event and excellent organization. We would like to present to you Lignovolt. So I think we all share, and I saw that in the other presentations, we share this vision of making wood a key resource of circular economy and a more sustainable future. And what we think is important is that we are able to also extend the fields of applications of wood to be able to substitute less eco-friendly materials. In this project, Lignovolt, we want to work towards a bio-based piezoelectric device. And you may think, okay, wood and piezoelectrics, does this go together well? So we believe it does. It mainly depends on the right ingredients and also on the recipe that you apply to make an interesting hybrid material. So I would like first to present to you our team, our core team of this development. Maria and Jonas, they are both chemical engineers. Dan, who's with me on the stage, he is a material scientist, and I'm a wood scientist by training. So we have a complementary expertise in the team, which is also important because we address very different scientific disciplines. First, let me give you some introduction into the fundamentals. So if you look into piezoelectrics, these devices are very commonly used in many modern devices like mobile phones or consoles, and they're mainly about functioning as sensors or in terms of haptics. So what is the principle? So you can, with piezoelectric elements, you can convert mechanical energy into electrical energy or vice versa. And this allows you then to go towards applications in terms of sensing or even energy harvesting. So although piezoelectrics are more known for low energy gains, there's a certain development at the moment. And here we would like to cite just one large project for large-scale energy harvesting, which is currently planned in California, where they would have piezoelectric elements below the pavement of a road. And so their calculations is that they would be able to gain 73,000 kilowatt hours per year on a distance of 1 mile of a one-lane road. So there are possibilities also for larger energy gains, but it depends a lot on the way of how you assemble and organize your piezoelectric elements. But there's always a but. If you think of this nice way of just generating energy by movement, and this but is about the ecological aspect to do this. So as already mentioned in the video, so the common material are lead, zirconate, titanate elements, and they are, because of the lead, they're seen as toxic. We have also, in general, a very low recycling rate of only about 70% towards electronics. And there are also not other sustainable alternatives in place at the moment. So therefore, we need greener alternatives for high performance. And if I think about green and high performance, the answer for me is wood. Yeah? And this is what we would like to develop in this project. So first of all, to become more green and sustainable in the approach, is also important to look into what we can use in terms of natural piezoelectrics. And if you look into the piezoelectric constants for various natural materials, like quartz or egg proteins, collagen also is an opportunity. Also cellulose in wood has, because of the semi-crystalline nature of cellulose, has some responses here. Or ammonium dihydrogen phosphate is known as a crystal that can be utilized, but our true champion is Rochelle salt in the way of how it could be explored. And Rochelle salt has not only very good piezoelectric constant, but also some other, we think, very interesting features, because it is a byproduct of the wine production. So this means if you enjoy a good glass of wine, you can also contribute to more sustainable energy harvesting maybe in the future. What is also a big advantage is that already streams exist to explore this. So in pharmaceuticals and also in the food industry, this is already used. So we would just add another stream for its utilization. But there are even more advantages. It comes with very low cost as a byproduct. And also the production is low CO2 emission. But again, there is a but, and in this case, it's brittleness. And that's why, although the properties are very excellent, it has not been utilized that much in piezoelectric elements so far. But here, now wood comes into play, because wood is a porous structure with very good mechanical properties. So the idea is now to make a hybrid which combines the best of the two worlds. And what we have done in this direction initially will now be presented by them.
Thank you, Ingo. And thank you to the members of the jury and the audience for granting us this amazing opportunity. So how do we overcome the limitations of this natural material, shell salt, and merged it with wood, another natural material, to create the first fully bio-based piezoelectric device that we named Lignaboard? And as we published in the Advanced Functional Materials Journal, our strategy starts by precise lasering of the wood to get a wood template. This wood can be poplar or other underutilized woods, and this will then allow us to use the wood as a mold to grow the ferroelectric Rochelle salt. The interaction is very good, and then what we need to do is extract the electricity. And we don't only want to have a bio-based piezoelectric device, we want to have a bio-based device, not just composite. And hence we use a fully bio-based ink developed also in our lab. And we do so by just simply applying a paint, like you saw Maria doing in the video, and then we lase the device to have catalyzed carpetization. This work was not done alone, but we did it together with InnoSwiss and with the Bauwerk group. And if we look back at the second step, more strategically at how this crystallization works, we can see that when we're, the laser drilled wood allows for, first of all, a very porous structure that we create, and then we use a hierarchical porosity from wood to then grow the Rochelle salt through the wood template, and we're having a very good interface between the Rochelle salt and the wood. This allows us then to overcome the brittleness of Rochelle salt, as we explained. So if we move further, when we go into this bio ink, we wanted to have sustainable electrodes, moving away from metals or silver, for example, that's very much used in the industry, as well as moving away from adhesives or fossil-based polymers. So this we did by first using shellac, a resin excreted by bugs, tannic acid, which we extracted from gallnuts, and we mixed it together with iron to create this very black bio ink that you can see. We then paint, we graphitize it with a laser, And then we obtain our composite, which is conductive on the surface, and current collectors as well, made from wood with a conductive surface. Well, I've shown you the natural origin of everything, but how does our performance compare? So when we compare our performance of Lignavol to commercial standard PCT, it's very difficult to choose a specific assessment method, and we chose the tapping methodology, in which when we tap and charge a capacitor, we can see that the voltage that we're charging, it goes up to, we can see that Lignavol can clearly compete with its commercial standard coin cell PCT that we chose to compare in this video. And what we were most interested to look at is how our performance evaluates with different strengths, because that's what will be key to know how we overcame the brittleness of our shell salt. So the strong crystal interface enabled a very good high signal quality and high voltage performance at high forces. When we increase the force, we can see that the voltage output was scaled almost linearly. And when we do repeated taps, we can see, and here, but we also showed in the journal, that we obtain very constant results, and hence we have a very good signal quality. And once again, this is from completely natural products. But how can we see this? And maybe we can go back to what we saw in the video, is that when we light up 60 LEDs, and this we did with just one device and tapping it with one finger, we can see that we light up the ETH zero total. And now moving on from natural and good performing, we wanted to do a fully circular economy design. We saw how we crystallize a natural product, we apply a natural electrode on top, but we wanted to revert the circle. We wanted to get back to the beginning and see that this was possible. So we first were able to remove the electrode and recycle and remove the shellac. We're using just processes at room temperature and ethanol, so easy processes, and fully reutilize these elements that we recovered. Then we removed the shell salt by dissolving it in water, and we're also able to recover these elements and as well as the wood piece was also fully recoverable. And we were then able to do a new device. And what was most outstanding for us was that we were able to maintain the performance after recycling. And what's for me very important is not only to use natural products, but to avoid with so-called greenwashing. So we wanted to look into a global warming assessment. And we wanted to look at the CO2 that our product emits and compare it to PCT for comparison. So we saw that from this assessment, in which we're just looking at the global warming potential, and hence I want to also remark that we're not looking at, for example, the lead components that can be leached from PCT, and also in this assessment, we didn't look at the recyclability of Lignavol, so this would just be in the production step. We had 60% lower impact than PCT. PCT was dominated by heat, while we were dominated by electricity from the laser processing. So we didn't say this was a win, but we wanted to further improve our properties, and this is what Ingo will explain next.
So here we already achieved a 60% reduction, but we thought we should go further when we think about how we would use the money that we could, in case we are awarded. And here it's clear we want to go in the direction of further improving at various ends, and our main focus would be on the scale up. So as a scientific group, the papers, the articles will come naturally, but the scale up is our challenge, and that's why we want to address this project. So the scale up relates to all aspects, the materials, the processes, and the design. So we see that we have still potential in improving the crystal performance. Also the electrodes and the circuit design is something where we would like to ease processes and also reduce the global warming potential, and that's why we will go for a process without lasering. I have to say, we love this lasering process from the scientific perspective, but we think in terms of implementation and also based on the calculations that Ben just showed, it might be not the most feasible way. And the same applies to the wood scaffolding. So here also we think we should go for a wood process which does not require the laser. And if we then take a revised global warming potential calculation, then we would be able to even decrease again by another 60%. So regarding the optimization of the crystal growth, to enhance the performance, it's about addressing other crystallographic accesses, and also the loading conditions can be still improved. And with this, we think we can expect about a 200% increase in voltage from what we already achieved, another 150% increase in current. And to show you also the process that we have done meanwhile, after the submission of our proposal, you see here, if it starts, yeah. So you see here this initial growth of the crystal in the wood structure, as we showed it before. And here's a way of how we can do it now with an optimized process. You hardly see it anymore because it's almost transparent. So that's why we added here this blue bar is showing you the developing front of this crystal growth. But also from the processing or the way of how we want to organize the final device, it's about enhancing the efficiency and also the sustainability in terms of the design and also the material combination. And so I give you here just an example of a kind of wood flooring aspect. So we would have the base layer, and here you have then screen printed electrodes on top of it, and we would add the wood scaffolding template, which can then be used to embed the crystals, which would come then after being individually blown into the structure. And this wood scaffold preparation, as I said, we don't want to go further with the laser, would be based on CNC. And then on top of this, you would need the second electrode, and then you would have, just as an example here, a floor which has this functionality and smartness of being able to generate voltage. So I talked in the beginning about the complementary expertise in our team, but we also feel we need more expertise in terms of electronics. So this is not our main discipline. Here we are happy that we can team up with Gerd Simmons, who's head of the Institute for Sensors and Electronics, Fachhochschule of Westschweiz. We have worked already with him together, and we would develop this further. And also the Bauwerk is interested also to developing further products. So we think about applications. Obviously, as I said in the beginning, it would be very interesting to be able to substitute PCT, to have an eco-friendly and high-performance alternative on the market, and use this, for instance, for sensor applications with highly sensitive devices. But the more thrilling point would be, of course, the energy harvesting for having clean, low-power energy generation. Would just like to specify a bit these two application fields. So if you think about sensing and functional smart floors, you could use this for data acquisition, for spatial planning. So compared to a camera system, this would be really anonymous, because you just record the step event, and it would be very accurate and would come also with much lower data costs. Another more very practical application we could think of is having our functional flooring in connection with smart homes. So you could have it below the window or close to doors. And if you're not at home and a thief would enter, you get a step-on event, which should not happen at this time. And then you would immediately get your alarm that something is going on. But as I mentioned already, so these are, I would say, even at the moment, I would see them as low-hanging fruits, as they could achieve rather easily, because it just needs a signal. The energy harvesting aspect is that what thrills us as a vision for the future, to collect the energy just from our daily movements. And here we think of particularly crowded spaces, like security check in airports, shopping malls, But I would say also a perfect dream would be a ballroom, yeah, where you have a sensing and harvesting floor, and just by dancing, this movement would generate energy. And how would we do this? So it's obvious we have to increase the power per square meter here, and but we can also follow the direction that was also taken in this project that I presented to you in the beginning from California. So if you do a multi-layer stacking of our lignovolt devices, then we would be also able to generate a sufficient amount of energy from the movement in these crowded places. So we hope to show you that, or hope we showed you that we have already the initial research to make the next steps. This project which we applied for here with Evergreen, and we would work further in the direction, as I said, of the upscaling to keep it sustainable in all process steps and go for a further performance increase to, in the end, derive at a vision of sustainable electrics for green electronics. So with this, I'm at the end. I would like to acknowledge the HS Timber Group, the Evergreen Prize, Bauwerk Group, and InnoSwiss. We are also already in contact with the Tanzhaus Zurich. They have next year an anniversary, and we agreed on that we work towards a prototype there that can be shown that it's possible, and of course the entire ETH and EMPA group, which supported us in all these steps. Thank you very much.
I have a question just to your last slides.
Yeah.
Do you have a rough estimate of the energy density or the harvesting density, what you can gain compared to a solar panel? You know, you have a solar panel, it's a different approach, I know. Yeah?
Exactly.
But a solar panel has about 200 to 400 watts per peak.
We checked it yesterday for Vienna. So the year average is about 200 for Vienna. So from our calculations that we did, I would say we can target something like maybe a quarter, ideally maybe half of it. But that would be really
okay. Yeah.
But so it can be really substantial. But it needs the stacking of the material. But this is about the rough numbers.
But if you take a shopping mall or something, and you have lots of people going there, and
Exactly.
you come half of the panel.
I mean, this would be really the upper range,
okay.
but let's say I would be more certain to say maybe a quarter of it. Yeah.
Okay. Thank you.
Thank you for a nice presentation. I have two questions. One is if there is any moisture sensitivity of the developed electrons, and the second one is if there is any wearing out, in terms of like how long it can actually last. And since you nicely presented also like recycling of it and coming back to the beginning, so I wonder if there is a certain number of cycles or time
So the moisture aspect, of course, also is always relevant when we talk about wood, but in this case also related to shell salt. So we have seen that the performance becomes problematic at something like 85% relative humidity. But I would say water and electronics is a problem anyway. Yeah. So I would turn it more as an asset that because we have this water related aspects that we can in the end more easily degrade and recycle the entire device. And regarding the durability, so we had 25,000 cycles. Yeah, maybe you.
So we tested 25,000 cycles of continuous pressing, which may sound like a lot, but it's still like in a device like this where we want to use for a long period of time, is still not what we want to do. And we also tested after we published 100,000 cycles, and we didn't see any major deterioration of the device. And so now we want to go for even further to like really show that it's a.
What we also should add is, so for the moment, we work with a maximum of 200 Newton.
Yes, exactly.
So,
I mean, we also tried out 500 newtons and the device doesn't break. Of course, this is 200 newtons in this small device, and when we're thinking about the weight of a person, it would be spread over more area, so it would be equivalent to around the 200 newtons or less.
I have a question about, again, scalability, commercial manufacturing. You talked about CNC. Have you looked at the cost of big volume manufacturing versus the existing solution? And where do you compare that?
so let's say what is very cheap is a material that we use. So we made a calculation that the single device, is a very small device that we produce, would be less than $1. I have to say for the upscaling, it's very difficult to have concrete numbers yet, because we have to see how we stack it. You know, this would be still work to do, but what we try to show you is that we have already several ideas how we can ease the process, how we may also be able then to have automation in the process, like with the CNC milling, but also with the individual crystal growth, so that we try to be as easy and lean with all the processes.
And if I can add, Rochelle salt, the cost of Rochelle salt per kilogram is around 10-fold less than PCT. So it would be even more dependent on the purity that we need. So then it's also just from raw materials, we're already cutting down the costs.
You still have 2 minutes.
Okay, I'll take one quick question. It was about the recyclability and you said it maintained performance after recycling. So just can you explain that to me a little more? Because you've broken down the component parts and yet it's maintained performance. So what performance is it maintained?
So what we break down the component parts and then we rebuild a new device out of the original device. So like we really try to be as faithful to like, can we make one device out of one device? And so when we did the full circle, as we mentioned, there's a slight loss of Rochelle salt, which we had to add. But apart from that small 17%, which we want to increase further in future scalates, when we tested the device again, we got very similar performance. We don't want to say the same performance because we don't have statistical packing up and you can do enough recycled samples, but the samples that we did recycle.
It's a bit less, but we are.
I think it comes to imagine how much movement energy must be there during harvest enough energy. We have thought about to include that in the structural system of the building maybe and harvest the energy of the wind for the movement of the building or something like this.
Could be also, as we have seen how it scales with the forces applied. I think it's much easier to go via this movement in terms of
talking about 50 watts per square meter, for example, peak. And it means that's about what a cyclist on each square meter in a room cycles all the time.
I mean, 50 kilowatt hour per square meter. So a kilowatt hour. So the unit of energy in solar panels, for example, is 150 kilowatts hour produced in average in Vienna per meter squared, and for our device we calculated 50 kilowatt hours per meter squared per year. So because it's very confusing units, also for us, I think, since it's also not our field, or was not our field.
Okay, thank you.
Sorry.
Time is over.
That's it. Thank you, everyone.
I can already see the masterpieces coming out, how much energy harvest you have, depending on the dance style. When I took my waltz lessons, I was told to hover above the the floor and not stomp on it. As a double, maybe that's good answer. Yes, thank you very much. I think this was 5 excellent presentations that we had today, and I really think the hardest job now comes for the jury, who have to make this already shortlisting shorter. Thank you to everybody for giving your presentation. After having met you and having watched your presentations, I'm certain that we invited the 5 correct and right teams to come here to Vienna. Everybody of you has had really a reason to be proud of themselves. It's great what you have achieved so far, and I hope to ask for another round of applause for everybody today. Again, thanks for TVB for providing the facilities here today. And thank you for the jury, but your hard part will come now. We will end now the live stream. So also thank you very much for everybody who participated online. By tomorrow, I think we're going to publish then the winner, or I think somebody
Probably at midnight.
might
Let's see.
During the evening. Very good. So.